Greetings, Chem Fam. We are going to learn about what a limiting reactant is. First thing, when you have a balanced equation, the reactants we know are on the left side. When you mix them together and a reaction occurs, most of the time, one of the reactants will run out first. So a limiting reactant is the reactant that runs out first. Because it runs out first, that will be the specific one that determines how much product is made. Why? Because if it's the reactant runs out first, there's no more reaction that can occur. So once you use up all the lowest amount of material, that's how much product you would be able to make. All right, so let's kind of dig deeper into this and see how we can solve these problems. So if you notice, I wrote down a few step-by-steps. First, we're going to write a balanced equation, then determine which reactant will run out first, and then we can identify the limiting reactant. But before we can do that, let's write our balanced equation. So we want to know what the limiting reactant is if we have this many grams of sulfuric acid, H2SO4, reacting with 5.92 grams of sodium hydroxide to produce sodium sulfate and water. Now, through that, we can write that equation. Sulfuric acid, H2SO4, is going to react with, so we're going to add it in the chemical equation, to sodium hydroxide. And that is going to give us a product of sodium sulfate and water. Water's H2O. All right, easy enough. We do want to balance that to make sure it's okay. There's 2 sodiums over here, so let's do 2 over here. All right, now let's see. We have 1 sulfate over here, 1 sulfate over here. That's balanced. We have, let's see, 2 hydrogens over here and 2 hydrogens over there is 4. So we probably need a 2 here, but that would give us 2 oxygens as well. So let's see, do we have 2 oxygens? Yes, 2 and 0. Perfect. So we have it balanced now as 1, 2, 1, 2. Now that we have it balanced, we want to determine which reactant will run out first. To do that, it's very simple. We're going to take each reactant and we're convert them both to the similar product. So since I don't care which product I'm going to find, I'm going to take the one that's easiest to solve for. So I'm going to look for water, H2O. So here's what I'm going to do. I'm going to take my reactant of 6.33 grams of sulfuric acid, H2SO4, and I'm going to take my 5.92 grams of sodium hydroxide, and I'm going to both convert them to water. If I know how much water is made, how many grams of water, and whichever one makes the least amount, I know that will be the reactant that runs out first. Whichever one runs out first will show me what my limiting reactant is, or the one that runs out first. Okay, so let's do that stoichiometry problem really quick to go from these guys, which are mass A, we'll call them, all the way to mass B, which will be our water. Again, could you have done it with sodium sulfate? Absolutely. I just chose water because it's quicker to find the mass for, and we didn't need to know the final ending, so this was a good place to start. All right, so let's do that. Step number 1, I'm going to take 1 mole of the substance, H2SO4. I'm going to divide it by the mass of the substance. When I add that up, sulfuric acid is about 98.09 grams for H2SO4, 1 mole of it. And for sodium hydroxide, for every 1 mole of it, NaOH, there is approximately 40 grams. And how did I get that? I looked on the periodic table and I added up each individual element. All right, now I'm converting to water, so I need to do my mole to mole conversion. To do that, I know that I have to put what I'm looking for on top, 2 moles of H2O, and that's going to be for this one as well, 2 moles of H2O. And now on the bottom, I need to get rid of sulfuric acid. So for H2SO4, looking at this balanced equation, there's 1. So there's 1 mole of H2SO4. And for sodium hydroxide, there's 2 moles. 2 moles NaOH. All right. Now this is just a stoichiometry problem, something you already have down. We're going mass to mass, so no big deal. The last step then is to multiply to get the mass of B, which is water in this case. We're going to multiply by the molar mass of water, which is 18.02 grams. 18.02 grams of H2O. And we are going to put on the bottom the moles of whatever it is we're getting rid of, which is moles of H2O. Again, if you're not following this conversion, this stoichiometry, that has nothing to do with limiting reactants. That's the stuff that we've already learned about, which is stoichiometry. So I would encourage you to go back and look up how to do a mass A to mass B stoichiometry problem. Okay, so now that we've had that, let's go ahead and plug out our answers to see what we get. All right, if I do the math, I end up with sulfuric acid all being used up, I should get about 2.33 grams of water if I plug this in my calculator and I use up all 6.33 grams of sulfuric acid. If I use up all 5.92 grams of sodium hydroxide, put that in your calculator, it says I would make about 2.66 grams of water. All right, so by using our stoichiometry, we figured out that if we use all sulfuric acid, we make 2.33 grams. If we use all sodium hydroxide, we make 2.66 grams. Well, which one do you think naturally runs out first? Sulfuric acid, which estimates to make less water, or sodium hydroxide, which is estimated to make more water? Well, think about it. The one that makes the least amount of water is the one that would run out first. Therefore, sulfuric acid is your limiting reactant, which is step 3. Which one is the limiting reactant? So since sulfuric acid makes the least amount of water, we would say that sulfuric acid, H2SO4, is the limiting reactant, Lr. That means it will run out first and you will have excess sodium hydroxide. So we could say excess NaOH because the sodium hydroxide would not run out. Sulfuric acid would. Okay? So hopefully that makes a little bit of sense. We will try our next problem to see if we can determine how much product we will get at the end. Example problem number 2, we're going to do the same thing. We are now going to write the balanced equation. So we want to know what mass of iron. So in the end, we are going to want to find grams of iron, okay? What mass of iron will be produced when 21.4 grams of aluminum is reacted with 91.3 grams of iron 3 oxide to produce aluminum oxide and iron? All right, let's write that balanced equation. It says aluminum is going to react with iron 3 oxide. And that's going to create aluminum oxide, Al2O3, and iron. Let's balance that equation out. There's 2 iron over here on this side, so we'll make it 2 iron over here. 3 oxygen over here, 3 oxygen over here, 2 aluminum. Let's put a 2 there. So this becomes 2, 1, 1, 2. Easy enough. Our next step now is to determine which reactant will run out first. To do that, I will take both reactants that I have values for. So I have 21.4 grams of aluminum, and I also have 91.3 grams of iron 3 oxide, Fe2O3. Now, because I know I want to eventually solve for grams of iron, I'm going to set both of these equal to grams of iron so that whichever one creates the lowest amount, I know that's the one that runs out first. That would be the limiting reactant. And I would also find out what the total iron would be because you have to use the limiting reactant to determine that. So I'm killing 2 birds with 1 stone in this step. So let's do that. Step 1, let's take this one. And instead of bouncing back and forth like I did on that last problem. Maybe I'll just do one at a time. Maybe that would be easier for you guys to follow. So I'm going to convert my grams of aluminum to grams of iron. So aluminum's mass is 26.98 grams for 1 mole of aluminum. So I'm going to put that for every 1 mole of aluminum, there's 26.98 grams. Now, to go from mass of A to moles of A, I'm going to get rid of moles of A, and now go to moles of B. So for every, 2 moles of aluminum from the balanced equation, I now get 2 moles of iron. That's easy enough. And now I want to get rid of moles of iron and go into mass of iron. So for every 1 mole of iron, there are 55.85 grams of iron. Again, why did I do a mass-to-mass stoichiometry problem? Because it's going to let us predict how many grams of iron are found at the end. In this case, when you put this in your calculator and pause and try it out yourself, you end up with about 44.3 grams of iron if you use up all 21.4 grams of aluminum. But we don't know if aluminum will run out first or iron 3 oxide, so let's try it out. Let's get our mass converted to mass of iron. So we're going to get rid of iron 3 oxide, and we're going to divide by how many grams iron 3 oxide is. If you add up 2 irons and 3 oxygen off the periodic table, you get about 159.7 grams of Fe2O3, which is iron 3 oxide. Now, use my stoichiometry and balanced equation. I know for every 1 mole of Fe2O3, according to my balanced equation, I get 2 moles of iron. 2 moles of Fe. All right? And now that I'm in moles of iron, I'm going to convert that over to grams. To do that, I know that there's 55.85 grams of iron for every 1 mole of iron. If I throw that through my calculator, and pause this at any time to catch up, but throw in your calculator, see if you get the same answer, I end up with about 63.86 grams of iron. Okay, now here's the big question. First of all, how much iron is really going to be made? Well, if all aluminum is used, you make 44.3 grams. If all iron 3 oxide is used, you make 63.86 grams. Well, the winner, of course, is the one that makes the lowest amount, because that means that after the least amount of reactant runs out, you are only going to get that much product. So that's how much of the mass you will actually find. So what does that mean? That means over here, aluminum. Aluminum is your limiting reactant, and that means that Fe2O3, or iron 3 oxide, is in excess. We have extra of it. There'll be some left over because after the aluminum reacts, there'll be some leftover Fe2O3 that doesn't get used. All right, so this is talking about limiting. All right, so we've been talking about limiting reactants. Of course, we need to balance an equation, predict with both reactants or the same product, whichever product is created the lowest amount of, that identifies what the limiting reactant is. And of course, since the limiting reactant runs out first, that determines how much product is made at the end. All right, ChemFam, hang in there and watch other video examples if you need some more help. I've linked some online.